right, cool. Welcome back. How's it going? Another week. Off to a good start. At least we're here. We gotta show up. It's like 90% of life. Just show up. Everything else we can figure out along the way. Anything interesting, weird, wacky happen with numerical methods or homework or reading? Questions? No? What error was it?
It was returning the augmented matrices. So, like first problem 1.3.
Yeah.
Problem 1.2.
Yeah, like coming into down here. Do I have, here's like a Gauss naive, load that one in. So one thing, like last section, we did run into a problem with this Gauss naive. Oh, why did that? Oh, because it says Fi. There we go. Let's try this. Where we had this value error, and like this is something that comes up. This can come up pretty often, like once in a while. I don't know if it's often, but it happens when you're trying to do something interesting and cool. You hit errors. If you're playing it safe, then you won't. Yeah, maybe you'll avoid errors. So in here, where it's telling us like, hey, setting an array element with a sequence, like, all right, well, I don't know what you're talking about. And then if I scroll up a little bit more, it's giving me this warning. So anything that's like a big red or kind of pink banner like that, it still did what you asked it to, but it's telling you like, hey, you might not be getting what you think you're getting. Like, I don't think you're using Python the way you think Python should be. No, like, I don't think that word means what you think it means. So usually, at least this is the old school, like my method of checking things is like, all right, what does A look like? A is the 3x3 array, so that seems fine. What does B look like? Because that's my other input. B is a one-dimensional array where the second value is another one-dimensional array. That's gonna cause some weird issues. So NumPy did it, like it did what I asked it to, but it's gonna cause issues with a lot of things that are expecting just a simple 1D array. So instead of saying like, all right, well, I want B to be all of these values, just give it one value at a time, so that I can say like, all right, well, let's try just F0, so that now B is just 0, 100, 0. And now when I look at my output and my augmented matrix, I get one vector and one augmented matrix, and it all seems like a little more kosher. And I'm not getting those big pink banners that say, "Are you sure you know what you're doing?" Like, back off, Python. I know what I'm doing. Sometimes. So that might have been a different error than what was coming up last week, but that was one thing that I was thinking about. The time-honored tradition of just print your variables and see what they look like to see if they are what you think they are. Anything else happening? Check in, see what's going on. So we were just taking a look at like trying to reproduce numbers. I don't know. What I get for like for 1,000 newtons of force, that the internal force in that member is like negative 150. 15 over 100. Yeah, I don't know. Oh, are you using beta over 2 or is it cosine?
Is it supposed to be like cosine beta over 2, or is it cosine of beta over 2?
It's a good question now that I'm looking at it. Let's do a quick, because that's probably a chat GPT problem, right? Because I just copied it over. So f cosine theta plus P2 cosine, that should be a beta over 2. I think mine is wrong. That's what I think. That's what you get for copying and pasting. At least that's what I get for copy pasting. Because I think this is supposed to be beta over 2, not cosine of beta over 2. Like that. Then you get the same thing that you were getting, like 260, right?
Yeah.
I think mine was wrong. Well, it was definitely wrong. Because I said, ChatGPT, take this matrix, turn it into an array. And it did, but it didn't do the order of operations to maintain actual sum of the force diagram correctly. Yeah, because this really, we're trying to figure out like these components. Nice, good find. Yeah. Yeah. Okay. Great. Yeah. Oh, the machine? No. All right. Yeah. Okay. And the answers are all normal. Yeah. Yeah.
doing the node composition of A, but I think that's a pivot matrix. Yeah. That one's showing you like how optimum row reorganization. So like what we did in class was like switch row 1 and 2, and Gauss works on sending that solves rearrange all of those. So ones that are you can rearrange your right hand side.
All right, so let's say we have big matrix A, we have some right-hand side vector B, and then we're trying to solve for all those unknown kind of reaction forces and internal forces. So A is defined, B is defined, and now I actually defined it with beta over 2, not cosine of beta divided by 2. So now I should have the correct left-hand side A matrix. And if I'm going to use the same matrix to solve multiple problems, and it makes sense to decompose it, turn it into L and U, and now every time I do Gauss elimination, instead of redoing that Gauss elimination, I can use L and U over and over. And do I have it defined? Oh, but that LU function, oh, and I already switched row 1 and row 2, that's okay. That LU function gives you a pivot matrix, a lower matrix, and an upper diagonal matrix. So the U matrix is the same output that you would get from Gauss elimination, just ignoring, it just doesn't have that augmented result. And then the lower matrix are all the factors that you would do during Gauss elimination. Then this first one is a pivot matrix that shows you how the rows got rearranged. So in this case, I already switched row 1 and row 2. So those are 1s on the diagonal. And then it took row 6 and row 4 and flipped them. So if I want to use that same reorganization, like if I have a, have it twice. Like in this solve LU, if I give it an L and a U, it's going to do a forward substitution and a back substitution to like give all the answers for X. Don't need to time it right now. But my lower and upper are L and U, and my right-hand side vector is going to be that pivot matrix times B. So it's rearranging that right-hand side so that it's in the right form. And then I get the result that -25, 174. So I'm just taking that pivot matrix, and instead of saying that PLU equals A, it's LU is the pivoted A, so then pivot times B gives me that new set of equations, kind of renumbering them. Instead of 1 through 6, now it's like 2, 1, 3, 6, 5, 4. Rearranging. That's the quick way of like plugging in that pivot so that it gets you the answer that you're looking for. And the nice part is because we're only rearranging rows, all these outputs are still in the same order that we plugged them in to begin with. So it's still P123, R123. Sorry. Yep.
Is this supposed to be multiplied by 100 or 1,000?
That would, what did I just do? This one would depend on what my B matrix was, what my B array. All right, so right now it's just all factor of 1. So if I want to do 1,000, yeah, so if I want 1,000 multiplied by 1,000, so 260. So for 1,000 Newton force at a 45-degree angle, that internal P1 is 260. And instead of positive would be compression, so negative means like in tension, and it's tensile.
Is it supposed to return the same answer as 9,000?
It should give the same answer, right? Let's double check. Yeah, it should give the same answer. Because for linear algebra solutions, there should only be one answer, because it's all a set of linear equations. If you think of a 2x2 solution, it's where do two lines intersect, and they always intersect at one location, either one or infinite. That's kind of the two sets of answers that we can have. We can either have one value of x or an infinite number, because we're like solving when does one line lie on another line.
Yeah, I know. I'll see corrections. Yeah, that's okay. describing it, but not saying anything. They have people that the number one field dimension. Yeah. Like it's just a scale value. But L should be two dimensional. So when you click that, it keeps auto saving. I love these options. Thank you. Yeah. I mean, at least for the line bad, like negative. Oh, are you using sort of LU from LU? So I think because E was in the original one, that would be like full building. So you're switching. Maybe you're wanting this is a Those are so for 1,000 it's E1 stretch 260, 260, E2 is stretch, stretch. Sometimes the output is what we want, but in this case, it's all those
So this is kind of like the process, describing some of the process of like setting up linear algebra and then post processing your result. When we have these, let me erase some of this stuff. So we have this problem set up where I know the force, I know what the constraints are on the problem, and I'm doing sum of the forces equals 0 at every corner of this truss. I could have made it as big as I wanted, right? Like I could have made like a whole bridge and figure out what the forces in every point in the bridge are, and then ask like, all right, how much stress is there in a single member along this bridge, or like what is the max stress, something like that. So when I get this answer, when I say like, all right, F is 1,000, and here's my constraints, then I end up with all these different answers. But the original question was, how much is this thing? Is it under compression? Is it stretching? What's going on? So I'm going to solve the whole problem. I get an answer for all 6 values, all the reaction forces, all the internal forces, and I'm just grabbing this one, like 260. But for 1,000 newtons, there's 260 force. So that gives me like one data point. 1,000 newtons, negative 260. sometimes, like, there are cases where you might care about all of the values, but a lot of, but you might not plot them all as like, okay, here is force throughout this thing, like in this output vector. Like a lot of times you care about how the inputs or something is changing, how it affects your solution. Anyway, a little bit of like solving and post-processing talk, which does lead into like the main steps of finite element CFD and finite elements. Like it's all the same kind of process. Set up the geometry, like all the meshing part, solve it, which is our main like linear algebra solution process. So in this case, we're looking at Gauss elimination, LU decomposition, and then the last step is post-processing. What do you do with those results? How did you set up the problem? How do you plot it? How do you interpret it?
Oh, yeah, okay. Okay. So you already did one step, which was this setting the denominator, but still control the first row. First row is just header of it. This is stress. So you add another process after, and then you can comma, and so skip rows, and then you can all one word.
All right, just a couple of minutes left in class. So, quick public service announcement. There's never ever a reason to invert a matrix. It's just, it's always, you end up storing a lot of numbers and it's computationally difficult and it's never worthwhile. Like, so we've done like LU decomposition. That's as close to inverting a matrix as you'll ever need for a computer. This is different than like doing things by hand. If you're doing things by hand, then sometimes it does make sense to invert the matrix because now you as a human, easier for you to kind of process. But on a computer, there's never ever a reason to invert the matrix. So what do we want to do? Make from numpy dot random import default RNG. So in practice, we're getting the same result from both of these. Like one, I make 100 by 100, and I'm solving for 100 x values, and it takes 200 microseconds. In the next one, I'm doing exactly the same thing. I'm getting the same exact result. It's just I'm storing the inverse and then using that to do the process. And let's see how long that one takes. Roughly no, like 60% longer. And the bigger matrices, like it never ever saves time to create the inverse and then do that. So the bigger these things get, the worse things get. So there's no algorithm that will ever invert the matrix and then solve and then like do the algebra. So 22 milliseconds, 30 milliseconds. So it's always like an extra 30% longer, or like 50% long, sorry, 50% longer for no reason. There's like we did the exact same thing. And the linalg inverse is a pretty quick inversion process, but yeah, we just don't need it. And these are pretty dense matrices. It gets even worse when we have like sparse matrices. Like if you have like tridiagonal or anything like that, then it's really easy to do Gauss Gauss elimination, but very difficult to invert the matrix. Yeah, do I have like K defined up above? Yeah, like this K matrix. This one, we can solve it pretty easily. So I have K defined there. And if I look at the inverse of it, I go from like a nice tridiagonal matrix to now a fully dense matrix where every term is filled up. And there's just no reason to like store all those variables for a nice, like easy to solve matrix that we had before. Anyway, that was my public service announcement. Pretty easy too. Just don't use INV for solutions. There's always a better way.